And welcome to SanfordFlipMath. This is AP Calculus. We are working from the Finney, Demana, Kennedy book, Calculus, Graphical, Numerical, Algebraic, and third edition. We're about halfway through the applications chapter for derivative, and we are looking at section 4.4, which is about modeling and optimization, and dare I say the two most dreaded words in probably all of high school mathematics curriculum, and that's word problems. Sorry, it's going to happen, and here we are. If you can't use this stuff, what's the point? You don't just have a toolbox in your garage sitting there just to have the tools. The math is the tools. Now we need a project. Well, here they are. These steps that you see here on the screen right now are adapted from page 219 in the calc book, in the calc book I just described, and pretty much the same stuff, just reworded a little bit and tightened up. So these are fairly common problem-solving techniques. This is not really specific to these particular problems. It's just a quick reminder about word problems in general. I'm just going to kind of recap these real quick, and then we're just going to get to it. Okay, so shockingly enough, in order to understand a word problem, you need to read the problem, identify important key information. Me personally, I like to take notes. Just a quick little summary of what you see. Circle things, draw on things, write things, whatever, preferably not in your textbook, but anything that is sticking out to you. Okay. Somehow from those keywords you should see something that gives you the impression that maybe we have an equation or a function that we're going to work with. In many mathematical settings we call that a model. So like for instance, area equals pi r squared is actually a model. It is a mathematical construct to talk about a way to put together what is going on with area for a circle. Okay, so the stuff that we're going to see mostly is going to be mainly about area, volume, could be maximizing profit, could be minimizing costs, could be something completely abstract, but most of the time it's tied into something that's, you know, physics or geometry related. Okay, very common that you need to do some kind of a formula. Okay, so formulas for area and volume and things like that are very appropriate here. Generally, it's useful if you look at some kind of a graph and think about what domain. Now, domain both from the equation, so if you're talking about a square root and you're not talking about imaginary numbers, then you can only take square roots of positives or zero. Maybe if you're talking about things with a fraction in it, you can't divide by zero. But also what makes sense for a situation. Like for instance, you're not going to have negative lengths. You're not going to have imaginary lengths. If you're talking about area can't be negative. So those are all things to consider. From those domain issues, sometimes you have endpoints. Most of the problems we're going to be working with are called optimization problems. Well, optimization or optimize means we want to do the maximum of something or the minimum of something. So usually these are maximum and minimum problems, and remember from the mean value theorem, if we're talking about a continuous function on a closed interval, you have to identify critical points and endpoints. So this should not be a shock. This is pretty much the only thing that is calculus specific in this list. And then lastly, you need to interpret it, or in other words, please make sure you answer the question. Okay, you need to put it back into the context. So if we're talking about maximizing profit, you need to be talking about money and kind of recap exactly what your answer means. Okay, all right, having said that, let's look at probably the simplest example that we'll see ever, and just to kind of get a feel for what's going on. Okay, and I've kind of recapped those steps here in a very tight manner. Okay, it says maximize the product. Okay, so I'm looking for a product, and we're not talking about like something manufactured. What we're talking about is from multiplication. Okay, so I'm just going to make a quick little note here. Okay, and what we have is as two numbers whose sum is 10. Well, that means I have two numbers that add up to 10. So maybe something like a plus b equals 10. Okay, so sum, as you know, means add. Okay, so this is a very abstract math example, but the idea is to try and make this as simple as possible to start out. Well, here's the problem. If I'm going to talk about product, if my two numbers are going to be A and B, I want to maximize profit, or I'm sorry, I want to maximize the product. Well, that product is going to be A times B, and I know that those numbers have to add up to 10. Well, here's the problem. How do I do a derivative on this? And I really have three, if I'm trying to do a maximum, I need a critical point or an endpoint. If I'm trying to find a maximum, don't I need to do a derivative? And how do I do that with two variables, two independent variables, two x-type variables? And then I have this product variable also. So the problem is, the thing is that I can't, at least not at this point. So what I'm going to do is rewrite this, and what I'd like to do is, since these two numbers, A and B, have to add up to 10, would it be fair to say that B has to be 10 minus A? Okay, so A and B are my two numbers. One of them is called A, one of them is called B, but B happens to also be equal to 10 minus A. And the thought here is that, if I have two numbers that add up to 10, could be 1 and 9, could be 2 and, and 8. And again, if I know one of the numbers, then I can subtract from 10 to get the other one. All right, well, sorry about that, but that's the idea. Okay, so one of the numbers is A. The other number is 10 minus A. Okay, so now this is the equation. This is the model that we're going to work with. Okay, I'm going to rewrite this as 10A minus A squared. And if you would rather use y equals 10x minus x squared, you're certainly welcome to. I'm going to do a little sketch here. I know one of the zeros is 0, and then the other one happens to be 10 minus 0. So 10 minus 0 is the other factor, so 10 is the other 0. And it's a parabola. It opens down, and it looks something like this. Now this problem is entirely about just numbers. So numbers can be positive or negative, numbers can be imaginary, numbers can be anything. So I'm really not going to say anything about the domain. And again, the only reason I'm graphing this is I want to feel for what's going on. And there should be a maximum. Now keep in mind we're graphing the product and we're graphing A. Okay, this is not X and Y. I mean, it is, but think about how these fit. All right. So I have this equation, P equals 10A. Try that again. P equals 10A minus A squared. I know some of you are going to rearrange that. I want to maximize the product, so I want to find the maximum. So I'm going to find the critical points, P prime 10 minus 2A. Critical points happen where the derivative is equal to 0 or undefined or doesn't exist for some other reason. 10 equals 2A, A equals 5. So that's one of the numbers, 5. Okay, maximize the product of two numbers whose sum is 10. Well, that sounds to me like it wants to know a maximum product. Okay, now before I do this, let me pop back here. Critical points, we have all of them. It's 5 and, well, 10 minus 5 would be 5, so this would be 5 times 5, so 25 is the y value or the p value. Okay, so I have the critical points. There are no endpoints because the domain is all real numbers and there's no reason to limit myself. And I need to interpret the answer. Maximize the product. Okay, so the maximum product is 25. Okay, so just a very speedy recap. I read the equation. I picked out that I needed to build in an equation, or I'm sorry, I read the statement. I needed to find an equation for product. So that's multiplying. Two numbers that add up to 10. So one of them was A, one of them was 10 minus A. I did a sketch of it just to kind of see what was going on, and domain is not really an issue for this problem because it's all real numbers for the parabola, and it's there's nothing about the context that says that we shouldn't have negatives or positives or anything else. Okay, critical points came from where the derivative equaled 0. Did that, solved it, got a equals 5 or x equals 5, and so the only critical point was at 525, product is 25, and then there are no endpoints, and we answered it. Okay, so that's it for that one. Okay, all of the examples that we're going to look at today, probably this one and one more, are fairly typical for calculus. Okay, and let me just rewrite this because what I did was snag this from Word without doing any kind of a equation editor. All right, so what we have is a rectangle with its base on the x-axis, and it's inscribed in that parabola. Okay, well, so a rectangle, its base is on the x-axis. Inscribed means it has its corners on. It's drawn inside the parabola. Okay, so I guess we need a picture of what's going on because this is a little hard to see. Now this could be, well, no, I guess it can't be. Never mind. Sorry. Y-intercept for the parabola is at 9. X-intercepts for the parabola are at 3 and -3. Something like this. Okay, so this is the y equals 9 minus x squared. Now, I don't know exactly where this rectangle is, but I do know that its base is on the x-axis, and I know that it's supposed to have its other corners on the parabola. Now, this looks kind of squarish. Don't get all excited. It might be a square, but I don't know. I just know it has to be a rectangle. Rectangle has to have right angles. Okay, and this point right here, I'm going to call it, cleverly enough, you guessed it, x and y. Okay, now what I'm supposed to do, now let me just make sure that we understand this. I have the parabola 9 minus x squared. Okay, that's that black parabola on the screen right now. I have a rectangle inscribed. I'm supposed to have one side along the x-axis, and I do. And then the rest of it is supposed to be determined by the rectangle being inscribed in this parabola, which means its corners have to be on the parabola. Now, the rest of this then, it says we're supposed to maximize the area. Well, the area of a rectangle is length times width. Well, and please understand, it doesn't matter which one's the length and which one's the width. I know some people, like in 3rd grade, get all excited about the length has to be the longer side, and then in geometry we learn that really that was boo-boo. It's not true. The length does not have to be the long side. Just because it has starts with the letter L does not make it length and long, and I know the words are related, but that is not going to be an issue here. Okay? All right, so what we need to establish then is I'm going to call one of these length or one of these base, and some of you I know learned this formula, base times height. That's fine. That actually applies a little more nicely. From here to here, this is the x value. And because of the symmetry of this parabola, wouldn't this side be the same? And therefore the entire length would be 2x, or the entire base would be 2x. The height, or the width, or the whatever you want to call this part, wouldn't that just be that y value? Okay, so notice I'm not using y here because it's about area, and this is about y. Now again, just like with the problem we did a second ago, we did that product of a times b, and so we had p, and we had a, and we had b. That was 3 variables. I really don't want 3 variables. I would like 2 variables. So I'm going to say 2x, and then y, the height of this graph, the height of this rectangle, or if you prefer width or whatever, length, width, it doesn't matter, is given by this y value, and y happens to be equal to 9 minus x squared. So here's the idea. I have this rectangle, and it maybe the rectangle is really here, and that would have a different area than a rectangle that maybe the rectangle's here, and I just don't know. See, the problem is I don't know which one would give me the maximum area. Okay, so I mean maybe it's supposed to be really, really tall and really, really narrow, but still within that parabola. Okay, so there are lots of different rectangles that could make this all work. Okay, so that's why we have to figure out which one works the best. Okay, so the area is given by 18x minus 2x cubed, as it were. Okay, and so to maximize this, we want to make this thing, as big as it possibly can. Well, so what we need to do is find critical points and endpoints. Now, endpoints would come from any issues from the domain. Okay, so quick little note here. If my rectangle was, let's say, wider, I'd have to go all the way to wherever the parabola was here, and I'm not really inside the parabola anymore. So my x values can't really be any wider than 3. Okay, so quick little note here. X has to be between -3 and 3. And again, because we need our rectangle to be inside this parabola, and rectangle inside, I just want to make this note for you as to why. So in other words, again, x equals -3 and x equals +3 are going to be endpoints. Those are things we're going to have to consider when we're maximizing and minimizing. Okay? All right, so that's kind of a domain issue. It's not the domain of the parabola, but it is the domain that makes sense for this particular problem. Okay? All right, so let's do critical points. So A prime. Okay, so I'm going to draw a line there so we know that we're changing gears here. 18 minus 6x squared. Okay, so I want this to equal 0 because that's where critical points happen, is where the derivative is 0 or undefined. This derivative does not have a place where it doesn't exist. Okay, so 6x squared equals 18. I really added 6x squared to both sides and then and then flipped it around. So x squared equals 3. X equals positive or negative square root of 3. Well, a lovely number to work with. Thank you so much, Mr. Sanford. Appreciate you picking that number. Yeah, by picking that, appreciating it, I mean not appreciate it at all. Okay, but those are where our critical points are. Okay, so now this particular problem would like us to maximize the area. Okay, so let's find what the area actually is for that point. Okay, so area equals, well, we have a number of different forms for this, and to tell you the truth, I think this one might be easier to work with. And that's just because when I square this square root, it's going to be nicer. Okay, so I think I'll use that. Okay, so 2 square root of 3, 9 minus square root of 3 squared. So this is 2 square root of 3. 9 minus 3 is 6. So 12 square root of 3. Okay, so this is the max. I'm sorry. This is where the critical point is. The critical point is at square root of 3, 12 square root of 3. Now, technically, this is actually, there are two of them. One's at a positive square root of 3 and one's at a negative square root of 3. But if you'll note, that's really the same rectangle. If this is negative square root of 3, or about 1.732, and at positive square root of 3, that was funny, again about 1.732. That's really the same rectangle, so it's not terribly exciting. And then we do have one other issue, and that's the endpoints. So remember, the endpoints happen at x equals positive or negative 3. So let's see what we get for area for that. Okay, so area equals 2 times, I'm going to go ahead and just do it with the 3 for now, and we'll see if we need to do the other one. 9 minus 3 squared. So this is 6 times 0, which is 0. I'm guessing that's a minimum area. for this context, because I'm not going to have less area than 0. Okay. All right. So what did the question ask for? It said maximize the area. Okay. So this is us interpreting and answering. Okay. I'm not going to say 0. The maximum area is 12 times the square root of 3. Now this was all based on a graph in a, so the context was not like a rectangle. I'm sorry, it is a rectangle, but it's not like your backyard or the floor space in a house or anything like that. So I don't really have any units to use here. I'm just going to make a little parenthetical note here that these would be square units if you were going to do that. All right, I am going to try and at least set up one more example. I'm not going to do the whole problem because I know time is getting away from us, but I'm going to set it up. Okay, and this one says an open top box is made by cutting congruent squares, from a 24-inch by 36-inch. It's a rectangular, I forgot to type in rectangular piece of cardboard. Okay, so this is 36 inches and this is 24 inches, and here's the picture. We've seen this before in pre-calc, but what we're going to do is cut a square from each corner, like so. So then, okay, this looks like that. I don't know if I can get at the top here. We'll try it. Hey, not bad. All right, and then what we're going to do is fold the sides up. Okay, so we fold it so that this corner and this corner come together. Okay, so when we're done with this, this is more of a 3D image. It looks something like that. And now the issue is this 36 was before I cut anything. And then what I cut, I'm going to call x. And since those are squares, the idea here is I cut off x from each end. So this is now 36 minus 2x. This direction here would be 24 minus 2x. Now I'm going to need you to pause this and look at this and make sure you make sense out of this. Okay, and then the sides that got folded up are x. Okay, open top box made by cutting congruent squares from each corner, blah, blah, blah. Find the size of the squares to be cut to maximize volume. Well, a volume for this is length times width times height. Substituting in what I have here, well, if I call the 36 minus length, 24 minus the width, and then the height, I'm going to call x. I want to maximize volume. Okay, so I'm just going to make a couple other quick little notes here, and then I'm going to kind of magically finish this. Okay. Okay, so far all I've done is multiplied everything out. Okay. Okay, there's derivative. Okay, so what I've done is I set the derivative equal to 0. And this is a big old ugly quadratic, and I probably could make this easier by dividing both sides at least by 4, maybe even by 12, but I just worked with it as it was. Obviously this is a calculator problem. So I set it equal to 0, did the quadratic formula, and this is where I'm at so far. Okay. Now, quick little note here. This is where endpoints come into play also. Okay. I want to go back to the original rectangle, or prism box. Think about this 36 minus 2x. Obviously, if this side was negative, this would be not a box. Okay, and that weirdness is going to happen when at x equals 18 here. Okay, so 2 times 18 would be 36. 36 minus 36 would be 0. In the same way, 24 minus 2x gets goofy at x equals 12. Okay, 2 times 12 is 24. So really, x has to be between 0 and 24, or 0 and 12, I mean. And I'm not going to have a 0 height box, and I'm not going to have a 12 width box. So really, 0 and 12 are not included either. So I don't necessarily need that written down anywhere, but I will say that it needs to make sense. So for instance, if I come back down here, this guy right here for x, although it's a valid solution for my equation, for, you know, for this quadratic that I just solved from the derivative, it doesn't make sense based on the context. Okay? So really the only one that makes sense is this one, 4.70849. And now remember what this is. This is x. So this is the height. Okay, so the height of this box, that is the size of the square cut. And calculus rules, AP rules, excuse me, would have us go to at least 3 decimal places. You could write the whole thing. You could write 3 decimal places truncated, which means just drop more decimal places, or you can round. This asked for find the size of the squares to be cut. Okay, so the squares are going to be 4.708 inch squares. It also happens to be the height, so I guess I probably shouldn't have written height there, but it's going to stay there anyway. Okay. Then the other part of this is to find the actual volume. Well, volume, remember, comes from this equation. Okay, so if I put in x equals 4.708, now you know me, I'm actually not going to put this rounded version in. I'm going to substitute in the value that's actually in my calculator, okay, the numbers that are there. Okay, so I'm just going to pause for. All right, well, there it is. Again, what I did was I put in x equals 4.708 with all of it with more decimal places into the volume equation, and just type that in, and I get a volume of 1825-ish. And again, this is cubic inches, it's volume, so there we go. All right, well, this went longer than I needed it to. Than I intended, and that's with pausing in between. Sorry about the length. But obviously word problems take a long time, and we will do more. Next video will be probably just a couple examples. Thanks for hanging in. Bye-bye.